We're going to do section 6.3, triple integrals in cylindrical coordinates. The goal of this section is to evaluate triple integrals using cylindrical coordinates. And essentially, these are polar coordinates with a z component. They can be very useful when the solid that you're trying to evaluate a triple integral over has a projection in the xy plane that's easy to describe in polar coordinates. So what do I mean by polar coordinates with a z component? Well, any point in the plane we know has an xy component and can also be described in terms of the angle theta it makes with the x-axis and r. So our point P here in the xy plane could be xy0 or it could be r theta 0. xyz, we understand exactly what that means. We go up a height of z to point Q above point P. Well, the exact same thing over P r theta, Q r theta z. The z is exactly the same. So it's really about how the xy are described in polar coordinates. The z component is just the same idea of a height either above or below whatever point you have in the xy plane. So proposition 6.3.1, if S can be described as all points in R3 such that the Z is bounded between two surfaces, U1 of xy and U2 of xy, and if xy in the xy plane is in a region D, where D can be described in polar coordinates in our standard way, as bounded between two angles and the radius bounded between the function of angles, then the triple integral over S dv can be written in cylindrical coordinates as the integral from theta 1 to theta 2, the integral from h1 of theta to h2 of theta. So far it looks exactly like a double integral in polar coordinates. Now we go to the z bounds, so u1, and we have to translate them. R cos theta, r sine theta, to u2 of r cos theta, r sine theta. And then our function f of xy also needs to be translated. So f of r cos theta, r sine theta, the z can remain. We have the r from the double integral in polar coordinates, and then dz, dr, d theta. So it looks like a real handful here, but really all it is an integral, the inner integral in terms of z, and then the rest of the integral in terms of polar coordinates. In the next video, we'll do an example and see that it really actually does make things much easier when the shadow of the region that we want turns out to be very nicely described in polar coordinates. See you in a bit.